We're going to go ahead and get started. So welcome to the CV4 review. On a scale of 1 to 10, how many of you guys have already attended CV4? I guess not a scale of 1 to 10. Raise your hand. I changed the question to a question. How many of you guys have attended CV4 already? Just you?
No.
No? Okay. Great. Well, we're here to review it. So what we learned about in chapters or lessons 11 and 13 are the differentials, so the first and second order derivatives, then our mean value theorem, and then our local extrema, so those mins and maxes, then your critical points, and then the concavity or end the inflection points. So those should be, that terminology should be kind of ringing a bell. Hopefully your teachers covered that a little bit. Yeah, next slide. All right, so extreme values and shapes of curves. So we have our absolute / global min and max. So basically this is, I'm not gonna read this word for word. It basically just says though that if a function of an input or the output of an input, if that's the greatest number in that function, then it's the maximum. It's a global maximum. Okay? So basically it says if f of c is greater than f of x for every single x in the domain of f, biggest value of the function, and we say it has an absolute maximum at the value c, we call f of c the maximum value of f. Okay? So that's just basically the biggest f can exist, or b. Then, if f of c is less than f of x for all x in the domain of f, the smallest function value, then we say f has an absolute minimum at c, and we call f of c the minimum value of f. And I forgot to remind you guys at the beginning, like this is your guys' review as much as it is ours, so ask any questions if you have any, stop us at any point. Does anybody have any questions about maxes and mins? Yeah.
What's the difference between like an absolute minimum and maximum versus a local?
Great question, thank you. An absolute maximum is the highest value. So this applies to maximum and minimum, so I'll just talk about maximum because it's easier for me to say. An absolute maximum is the highest value of any function. No, not of any function, of the function. And a local maximum is the highest value within a set range or set interval. So if you think about like a cubic curve, you know how it goes like from the bottom and it does a little squiggle and it goes back up? The absolute maximum is infinity, right? Because it actually never goes back down. But a local maximum is the kind of like the mountain peak. Does that make sense? So if we set like the interval from 0 to negative infinity, then there's a local maximum at that little rounded part. And same with the minimum, but when it's the lower value. Any other questions? Okay, next slide. Alright, so this is how we find our local extrema, is critical numbers. If c is in the domain of f, and if f prime or the derivative of f of c equals 0, or if it's undefined, the derivative is undefined, then at that x value of c is a critical point. At these critical points is how we find our absolute extrema. No, our local, either or. That's how you find the maximums and minimums. Either when it's undefined or when it equals 0. So in easier words, it's you find the derivative, you set it equal to 0, then you plug those points back into your main function to find which one's the biggest or smallest. Okay? That's what this says right here. And then as well, this is very important. So if we have a set or a set interval that the derivative is not defined at the endpoints, therefore the endpoints are critical points, and you need to test those values as well. Just plug them back into the function and see if they're big or small. So, yeah. All right, cool. So this is like, this should be an easy problem. I don't know if you'll have an easy this easy of a problem on your CVE, but we're just going to identify all the critical points on the following graph. So who can tell me what some of the critical points are just by looking at it? Yeah.
Just one. Or no, there'd be three.
Three, for sure.
Because there's the bottom, and then there's the top of the bottom one, the bottom of the top one, and then the solid point, right?
Uh-huh. So at x equals 3, because it's the endpoint, right? We want to test right here. So I'll put x equals 3. Where else?
2, and then 0. X equals 2 and x equals 0.
Why 2? Because x equals 0 there. How do you know that x equals 0
Because
there?
It's at the bottom of the div. So it's gonna be the absolute minima for that.
Nice. Yeah. So anywhere where the slope changes too, like if there's a valley or a peak is what we call it. I think that's actually the technical term.
Yeah, I think so.
That's what I always hear in class is valley or peak. Then x equals 0 at the top, and there will be a critical point there. So there's one more, or no, there's 2 more, right? Yeah, 2 more critical points.
So does -2.5 count because it's not included in the? I was pretty sure they don't count, right?
No, since the function can't like exist there because it's an open dot.
Doesn't count.
Yeah, we can't plug -2 halves, or that we can't plug that point into the function. What's it good? If it was closed, yes, you would.
So does 0 count then?
Yeah, 0 should count because that's a maximum, right? We had a minimum right here. We have a maximum right there. And then there's one more.
The x equals 1,
Why would it be x equals 1?
because it's undefined right there.
Exactly. So our derivative is not defined at the asymptote because the function is approaching 2 different numbers. Right? So there we have a critical point as well.
Cool. So the extreme value theorem. So it's kind of just saying that if the function is continuous, means there's like no holes or gaps like we saw with the asymptote, then it achieves an absolute maximum and minimum in the interval. So kind of like if we take a chunk of our function, there's a point where it's the highest and a point where it's the lowest. And then the absolute extrema occur at the endpoints of the interval or at a critical number between the endpoints. So either like one of the ends is like the highest or there's a peak somewhere in here. Same with the lowest. Questions on this one? Okay, so these are kind of the steps on how we find those maximums and minimums. So first you find the derivative. Then we find the critical numbers. And kind of like Aiden said before, we want to do 0 equals the derivative and just solve for x. And that will tell us like where our slope is 0. And then we can plug those numbers back into our function to see if it's like max or min, like if it's the highest point or maybe it's one of our endpoints. Questions on that? We'll do an example in a second.
Sorry, yeah. Any questions?
Okay, so this one's a little different. So is this true or false is all it's asking. Is the f prime at -4 greater than f double prime at -4? So let's look at, we're looking at -4, that's right here. So what's our slope at that point?
You can't determine.
Right, yeah, it's undefined just because it's a sharp edge. So, yeah, that's undefined, so we can't really say anything about this expression. So I guess you can maybe say it's false, but it's just undefined.
So we assume the graph is showing f of x. x, right?
Yes,
Okay,
yeah.
it's not-
So-
okay, got it.
Yeah, if it was like this point instead, our slope would be like 0. But because it's a point, we can't say anything about it. Okay. Questions?
That's such a dumb question. All right, problem 3. We're gonna find all the critical numbers of the function. So our first step is going to be finding our derivative. So it's this one's gonna be pretty straightforward. If you guys have any questions about finding a derivative, feel free to stop me, but I'll go through this pretty fast. So this is gonna be 12x squared minus 33. And so then we're gonna set this equal to 0 here. And then we're gonna have to solve for x. So I'm gonna move that 33 over. And so then I want to divide that 12 out. So we'll get x squared is equal to 33 over 12, which is also equal to, if I factor out a 3, that's 11 over 4. Then I need to take the square root of each side. So then x is going to be the square root of 11 over 4, which is equal to the square root of 11 over 2, plus or minus. Yeah? So then, now that we have our critical points, we want to know which one's a maximum, which one's a minimum, if they're either. And so you would plug them in, and then you would just compare them. This one would have local extrema at those points. So like I said at the beginning with the cubic function, this is like, these 2 points right here is when it goes like that. Yeah. So I guess should we plug them in? Yeah?
Yeah.
Okay, sure. So then we'll plug them in, and I'll just do the positive version. The negative version is probably going to give us the negative version is definitely going to give us the lower value. So I'll just do the positive one for now. 11 over 2 equals 4 of root 11 over 2 cubed minus 33x minus, oh wait, frick. Not x. Oh my gosh, that erased a lot. All right. 33 times root 11 over 2 minus 4. All right, basically, I know that this is going to be greater than the negative. I'm not going to simplify it for you guys, sorry.
What?
You can do that on your test. I know this is going to be greater than... This is the negative version because the cubed is going to be the main like driving force. And when you cube a negative, it still stays negative. And so then I know that f of root 11 over 2 is a local maximum. And I could also state f of negative root 11 over 2 is a local minimum. Okay. Any questions about the steps? Yeah.
Do we know if those, we just know that they're local, could they also be like absolute maximums and absolute minimums?
They could. So the critical points can be absolute extrema, but since I know this function and we're on the interval of negative infinity to infinity, I know that negative infinity is going to be my absolute minimum and infinity is going to be absolute maximum.
So if we were on a closed interval of like actual numbers, you would also include those numbers
Yeah.
as you would plug them in and compare them, correct?
Yeah.
Okay, cool.
Yeah. And then if you said like, let's say we're on an interval of 0 to 2, if you had you could say these are still local, and then those endpoints would probably actually be your absolutes. And on the interval. You have to say it's on the interval.
Cool.
Yeah. Yep. Thank you.
Okay, so this one, very similar. So what's our first step?
Find the derivative.
Yes. Okay. This one's kind of a funky one. It's going to use a product rule. So I would split it up like take the 3x as one piece and this e as another piece. So the product rule first times the derivative of the second, and it also has a chain rule in it, so it's a bit messy. The second, it looks like this little top part, this 2x plus 1, the derivative of that is 2. Then e to the 2x plus 1. And then continuing the product rule. So we did first times derivative of the second plus the second times the derivative of the first. So that's just -3. Are we okay with the product rule and the chain rule inside it? Okay, it's a little bit messy. Okay, and then next you can kind of do some like simplifying here. What I did is I made this a -6 x times e to the 2x plus 1 minus 3 e to the 2x plus 1. And this thing is hard to write on. Okay, so we're okay with that. It's just some algebra. And then what I did next is I factored this e section out. So then I can just have -6x minus 3. So remember, our goal is to set this equal to 0, and right now this is really hard to solve. So I'm trying to make it easier to solve. Minus 3, so that's one piece, times our e to the 2x plus 1. If I multiplied this back out, I would get this one. Okay, cool. So now this is a little easier to set equal to 0 to find our critical points. So this is 0. And what do we know about exponentials? Can the
It can equal 0.
right, it's like even e to the 0 is 1, so yeah, we don't care about this. It can't ever make this 0. So I'm just going to worry about this one. And then we do some algebra again, get -6x equals 3, and we have x equals 1/2. Okay, questions so far? Oh, yes, thank you. Yeah, -1/2. Okay. And then this one. So that's not quite what it's asking for. What do we need to do now?
Plug it in.
Right, exactly. So this is the x coordinate, but we need the absolute maximum, which is the y. So, oh yeah, and also it's good to double check that it's actually in the interval it gives you, which it is, so we're fine. Okay. Just gonna erase some of this mess. Okay. So we plug it in. Okay, and then this is 3/2 e to the -1 plus 1. So 3/2 times e to the 0, which is 1. So it's just 3/2. Oops, that was a messy box. Okay, questions on this one?
You guys are given a small calculator on the CD, right? That's included in the test. Like you click on the options or something.
Oh, yeah, that.
Okay.
That looked like
Okay.
physical.
Yeah, so I guess you wouldn't need to do that by hand, which would be nice.
It
Okay,
might be easier to do this one by hand instead of plugging it into your calculator. But
that's true, yeah.
Alright, so I guess we've kind of already gone over this, but just to refresh it. Sure. The local maximum is if you have the interval and like your function's curving, basically it's those peaks and valleys, so that local max is going to be that peak, that local minimum is going to be that valley, which basically means that you can always set an interval where that mountain or that peak would be the greatest number, if you include it, right? And same thing for the minimum, so I'll just read it. If f of c is greater than or equal to f of x for all of x in the domain of f lying in some open interval containing c, that is bigger than the values close by it, then we say f has a local maximum at c. If f of c is less than or equal to f of x for all x in the domain of f lying in some open interval containing c, smaller than the values close by it, then we say f has a local minimum at c. Any questions? No? Finding the local maximum and minimum, or minimum and maximum. They will always be at their critical numbers, so yeah. But not necessarily, a critical number is not necessarily a local extrema. To check if a critical number is a local extrema, we can use the first derivative test. And use f prime to determine if f changes from increasing to decreasing at those critical numbers. Yeah. Basically, you're just gonna plug in values to see if at that point around it, if your slope is going to change from increasing to decreasing. Yeah. Makes sense? Okay, cool. Problem 5. Wow. Concavity. So, if f prime of x is increasing on an interval, that is, if f double prime is greater than 0, that's the best information on this slide, I think, personally. It's less of a guess of check and more of you take the double derivative, and then you just see if it's positive or negative. That'll tell you if it's open, concave up, or concave down. So, then the function is concave up on the interval. If f prime of x is decreasing on the interval, that is, if f double prime of x is less than 0 or negative, right, that's just saying this is negative, that's positive, then the function f is concave down on the interval. An inflection point is a point where a function changes concavity, and it may happen, it says not always, but it's like almost always, when f double prime equals 0. So if you're ever asked for the inflection points, set your double or your second derivative equal to 0, and you'll find at which x values your slope changes from increasing to decreasing. Okay.
So on the last slide, sorry, at the end when it said like use f prime to determine if f changes from increasing to decreasing. So do you take your critical points and put that back into f prime? Like plug it into the x of f prime?
If you put your critical points back into f prime, you'll get 0.
Oh, yeah.
What I would do is test values around your critical point.
Yeah,
So like if our critical point's 1, I'm testing f prime of 0 and f prime of 2.
yeah.
And
And then like if it's like if it's negative at 0 and then positive at 2, then it's increasing.
Then at that critical point would be a local minimum.
Oh, okay.
Because you're at 0, if it's negative, that means your slope's decreasing, then at 2 is increasing, so you're gonna get like a parabola on that interval. Any other questions about the concavity? On the next slide. Alright, cool. Finding local minimum and maximum. Method 2, this is my preferred method. Just because it's less guessing checking, because like we can do the method that was just described, but it's not exact. Like you can have a function that does like a lot of tiny waves and then you're cooked. So I personally prefer this one. It's basically if f of prime of c equals 0, so that's a critical point, and then your second order derivative of that critical point is negative or less than 0, then it has a local maximum at that point. If your critical point and the second derivative is positive or greater than 0, then there's a local minimum at that point. Which basically means if your second derivative is negative, then it's concave down, upside down parabola, therefore we have a peak. If your second order derivative or second derivative is positive, then it's concave up, and we have a u or a parabola, and we have a minimum. That's how I think of it. In terms of parabolas, either it's a negative or a positive parabola. And then if f double prime of c equals 0, and no, f prime of c equals 0, and f double prime of c equals 0, then the test fails and no conclusion can be made. And then we get the results of the first derivative test again. Alright, I'm gonna have to use my notes on this one. This probably confused me. So, we're going to. Okay, well, so the problem is asking us with this function on the interval -3 and -2 to figure out if there's a local maximum, a local minimum, or if it's decreasing or increasing on the entire interval. So I know that we just gave you those two options. If you get a problem like this, it's definitely just the first derivative test because you just want to know what the slope's doing. We don't need to actually find it out. And then the second derivative of this function is like super annoying to take. So trust me, I did it and it's not very fun. So we'll take the first derivative here. Equals 2 plus, now I have to use the product rule and the chain rule. So it'll be, I'm going to pull the 8 out in front of everything. Sine 2x, so the derivative of sine 2x is cosine 2x times 2. And then that is also times our other part of the product rule, so cosine x. Plus, I'm going to write it below it. Plus the derivative of our second part, which is sine. Negative sign, thank you. My least favorite. I can never remember that for some reason. Sine of x times cosine. No, sine of 2x. That erases a ton. Okay. Yeah, and please correct me if I get anything wrong. Sine of x times sine of 2x here. All times by 8. Right? Did I do that right? Okay. Yeah, I'm just trying to remember it. I didn't actually walk through it in my head. So then we're going to test the interval points here because it just kind of gives it to us nicely. Because I've not, like, if you set this thing to 0, I'm going to walk you, like, I tried setting this to 0 and taking the second derivative, and it did not work. So the first derivative test is basically the only way to do this problem, I'm pretty sure. Because trying to find the 0 of all those trig functions is, like, impossible. So anyways, we're going to test this of -3. All right, so we're going to get 2 plus 8 times cosine of 2 times -3 times 2. I should have simplified this before I started writing. Well, cosine of -3 minus sine of -3 times sine of 2 times -3. Okay, and this is the instance where, like, You're just probably gonna want to plug it into your calculator on the test. I have the value of my notes, so let me pull those up real quick. No, I don't have the value actually. I just remember
My notes.
you do. I just remember it was positive. That's okay.
I guess I just wrote positive slope.
That's exactly what I
mind.
did too. Okay, so you're gonna have to take my word on this one. F of -3 is greater than 0. No, it's less than 0. Feel free to double check that if you want. And then we'll do the same thing for f of -2. 2 plus 8 times cosine of -4 times 2 cosine of -2 minus sine of -2 times sine of -4. And f of -2 is positive. Therefore, if I have a negative slope on one side and a positive slope on the other side, what do I have?
Local minimum.
How did you know it was a local minimum?
Well, I just like picture the concavity like negative to positive, and if you draw that, you can see the local.
Yep, exactly. Any questions on that question? Okay, cool.
So it has to be, you recommend using the first derivative.
Yeah, it technically would be possible, but like I said, trying to solve for 0, like if you set that first derivative equal to 0, it's just so hard because you have no idea. There's no inverse trig functions you can use, no trig identities you can use. And I'm an engineer, so quickest way out. But yeah, you could technically probably do it the other way, but this way would be easier, especially since like kind of like a thing in your head is like if it's asking you if it's decreasing or increasing on the entire interval, that's probably just staying in the first derivative. That's the slope, not the concavity. Yeah, thank you for your question.
Okay, so this one we want to find the x-coordinates for the local max and mins of this function. So we're going to show you one where we use the second derivative test. So first we want to get all our pieces. So the first derivative, so it's -1x plus 12x squared minus 36x, 6x. Yeah? Okay, sometimes my mental math is not good.
Your -1x is cubed, right?
Oh, yes, thank you. Yeah. Okay, then find the second derivative. We just do it all again. So you have -3x squared plus 24x minus 36. Okay, and then set it equal to 0. Okay, and looks like I can factor a 3 out of everything. 3. I'm actually going to factor a -3 out, so then the x squared is positive. My brain just likes that better. Oh, it's -8. Then plus, is it 12? Yeah, okay. X. Okay. Then when we divide this -3 by both sides, the 0 just is still a 0, so we can just get rid of that. And then we can factor this again. So we need something that adds to 8 and multiplies to 12.
X minus 6 and x minus 2.
Perfect.
Right.
So we have, it factors to x plus 2 and x plus 6.
Would it be
Which-
negative because your 8x is negative?
Oh, yes, thank you. Losing negatives all over the place. Okay, yeah. Oh. Yeah. So then when we solve for that, we get +2 and +6. Okay, are we okay with this? Okay, so now what do we do?
Would you take those 2 points and plug them back into your second derivative to see if it's concave up, concave down?
Yeah. So I'm gonna see.
Wait, speak up.
Would you plug it back into your first derivative? Because if you plug it into your second one, it'll equal 0 still.
Yeah, if we plug it into our second one, it's going to give us 0 because that's what we solved it to do, right? So then what we want to do is, we know these are our inflection points, right? Or at least our critical points. So what we can do is, if we plug this into our equation, and let me see what I was doing here. Okay. So if we plug this into first one, then we get, I think I had an error in here somewhere. Okay, I think it's fine. Okay. Does anyone see an error? Okay, I think we're good then. I think I had an error on here is the issue. Okay. Fourth. Oh, it just asks for the x coordinates, so we don't actually need to do that. So one thing you can do is, what it's saying, like, check that the concavity changes. It's saying, because sometimes you'll have an inflection point that isn't a min or max. So sometimes what I like to do is just go a little bit to either side and make sure it changed. So is that how you guys do it in class usually? Okay, yeah, so that's if you needed the y coordinates, but we don't. So I'm just going to take maybe, like, we have 2 and 6 are our points. So we need something to this side of 2. I'm just going to say 0 because that's easy, yeah? So at 0, we check our concavity, which is this second derivative. So -3 times 0 squared plus 24 times 0 minus 36 just equals minus 36. So concave up or down? Right. It's negative, so we have our sad face, concave down. Okay, now we need something between 2 and 6. Say 3 maybe? Okay, so -3 times 3 squared is 24 times 3 minus 36. And let me see if I did this already. Okay, I don't think I did. So that gives us -20. Okay, that's kind of a mess. Just steal this and plug it in. And you can do this on your test. So -27 plus 24 times 3 minus 36, and that gives us 9. Unless I typed something wrong. So that's positive, so we have our little happy face that's concave up. So it does change here. So that is a good point. And then something past 6, you could do like 7 or something. So negative 3 times 7 squared plus 24 times 7 minus 36. Yep, that gives us negative 15. So we have a frowny face again. So it does change at both of these. So those are both good. Sometimes you'll get like 2 concave up in a row, and then that point doesn't change the concavity. That's kind of rare, but it can happen. Okay, questions on this process? It's kind of a long, messy process.
So if that does happen, which is rare, you just don't include that number as one of your
Mhm.
answers for your way.
Right. Yeah, so if the concavity doesn't actually change, it means there's just like a weird like wiggle or something. Like a lot of times it kind of looks like a hump kind of thing or something like that. So it means it's not actually max or minimum. It's only if the concavity changes. We have that. Okay. Questions? Yeah.
So how would you use this to find like which one's the minimum and the maximum?
Okay. Yeah, so if we wanted to find like which ones were minimums and maximums, we could like if we plug the let me erase to get some more space. Oh, it just went up, moved on. What the? Yes. Okay. Well, it's not going to let me erase, but pretty much you would plug in the things we got, the 2 and 6, into this. And then if you check the concavity, and if it's, maybe it'll let me draw.
So you plug your 2 and your 6 into your original function or your first derivative?
So we plug this into our second derivative to see if this is like concave down or concave up, and then we can see if it's a maximum or minimum.
So your 2 and your 6 you'd plug back into your second derivative. I thought that would give us 0 though.
Oh, I just realized what I did wrong, why it didn't match. Okay, so thank you, you got it. Okay, so when it says set equal to 0, we want to set our first derivative equal to 0. There we go. Okay, I was wondering why it wasn't getting us the same thing. So we want this to be equal to 0 because that gives us our slope is 0, our max or min. That makes sense why what I did was wrong. Okay, so yeah, you're right. That would just give us 0 back, which is not right. So we want our negative x cubed plus 12x squared minus 36x to be 0. Okay, so I can pull a negative x out of all of these. Get x squared minus 12, not 21, 12x minus 36. Okay. Okay. And then, so this one will give us 0 for one of them, and then we can factor this further, and then multiplies to negative 36, and oh, this should be positive 36, and adds to 12, so x minus 6, and x minus 6. Everyone agree? Okay, and then, so that means x is 0 and 6. Okay, so then we check those with the second derivative. Okay, here we go. We're on track. Okay, so when we put 0 in it, we already found that was negative 36. So negative 36, that's concave down. So that means that's a maximum. So we have our little frowny face. Okay, and then 6, when we plug that in, and that's what I did on here, it ends up, we have negative 3 times 36 plus 24 times 6 minus 36. And this, it just gives us 0. You can double check with the calculator. But if it's 0, we don't really have a concave up or down. So that one's 6 is not a max or minimum. So we just have a 0 and maximum at 0. Okay, after my mess up, are we okay with how to actually do it? Okay, cool.
So first derivative, set it to 0.
Yes.
Actually means.
Yeah, because here the slope is 0, is what we want.
Yeah, so the first derivative is you're always finding your maximum or minimum. The second derivative is you're checking if they are maximum or minimums by the concavity. So whenever your second derivative is less than 0, you have a maximum. Whenever it's positive or greater than 0, you have a minimum. When it equals 0, you have nothing. And if you were to graph this function in Desmos, like x to the fourth has like a little wave at the bottom. And so that's where this critical point comes from, because it technically does equal 0, but since it's small enough, it doesn't register as a local extrema. And it's not like the best explanation, but that's where it comes from, if you guys are wondering. So, yeah.
Questions? Okay.
Okay, sorry. Just gotta remember every single problem every time I look at it. So, this one we're asked for the concavity. So concavity, second derivative. That's what you guys should think. You read concave, you're thinking, okay, I need to find the second derivative. All right. So our first derivative is going to be f of x, f prime of x equals 1/3. Oh my gosh, I hate this pen. 1/3 cubed minus x squared minus 3x. Our second derivative is going to be x squared minus 2x minus 3. Let me double check. Yeah? Did I miss multiply anywhere? Don't think so. All right. Then we're going to set this equal to 0. X squared minus 2x minus 3. Which this factors into...
Wait, doesn't set the first one to do?
That's a good question. So...
This is inflection points.
This one's asking for the inflection points, so we are setting the second derivative equal to 0. If it was asking for the minimum and maximum, then we would set the first one equal to 0. Thanks for keeping me honest. So this one factors into x minus 1. No, x plus 1 and x minus 3. So then our inflection points are at x equals -1 and x equals +3. Okay? So how do I want to test the intervals?
So I actually have a question though. So
Yeah.
so it's -1 and 3, and that's your interval then? Or are those just your critical points?
So those are my inflection points.
Okay, those are your inflection points. But those
So-
aren't your interval.
Think like this is where the slope, or no, this is where the function changes slope. That's an inflection point where it goes from increasing to decreasing. So think about x cubed is my favorite function for this. in the middle, you have where the u, the parabola, meets the upside down u, right? And mathematicians ask, where does the function go from increasing to decreasing? And that's what an inflection point is. Or more so, when does it switch from concave up to concave down? And when the inflection point is 0, or at the inflection point, is when that happens. So what we need to do is we have, kind of like Megan just did, we have our number line. We're gonna have -1, and then we'll have 3. And we need to test values at each of these. So let's test 0, 2, and 4. So if I do f double prime of 0 equals -3, huh? That's not what you,
If you plug it back into your second derivative, wouldn't those just give you 0 as well?
yes, but I'm not testing my
Oh,
inflection
you're not
points.
testing your inflection points,
I'm
you're just
testing
going
the
around
points
them.
in between.
Okay,
Yeah. So we need to find that interval.
yeah, makes sense.
Well, I think I did something wrong, so I may have to reference my notes pretty soon. Maybe I switched the.
Should be between the -1 and 3.
0, -1.
Yes, that's it. That's why I was like, I know the interval. I know the answer. I was like, that doesn't add up. Thank you, Megan. That was all right. That's fine. Just a minor setback is all. So let's test -2, and then this will be our point. So f double prime of -2. That's gonna give me 4 minus 4. Right? -2 squared is 4. Oh, that's 8 minus 3. So then that'll be 5. And f double prime of 4 is 16 minus 8. So that's 8 minus 3 will also give me 5. So then we know the interval. Since our second derivative is only negative at 0, and we know our inflection points, our interval is going to be at -1 to 3. Does that make sense?
So your graph would look like concave up, and then when it hits 1, 3, like that.
Yeah, so this is another x4th. So you have like a W.
Yeah.
It goes from the left, it goes down, and goes like that. And it goes back up. So, well, -1 to 3 is kind of like that W part, the top of the W. Yeah. Cool. All right, problem 8.
Okay. So we know that f of x is continuous everywhere. And then if f prime of 3 is 0 and f double prime of 3 is less than 0, then which of these are true? So f prime of 3 being 0, what does that tell us?
So your slope is 0.
Right, exactly. So our slope is 0 here. Slope is 0, so maybe we have a maximum or a minimum there. Yeah. And then f double prime of 3 is less than 0, so it's negative.
So does that mean that it's concave down?
Mhm. Yeah, so we have it concave down, the slope is 0, so yeah, we have a maximum here. So it's a local maximum. And then is it an inflection point?
Yeah, because the slope's changing. No.
Mhm.
No, it's not.
Yeah,
It's
so-
downside.
Exactly. So it's concave down this whole time. An inflection point is maybe if we have like that, it switches. So nope, not that one. It's not a minimum. Oh, yeah. And then, yeah, we do have some information. So it's just B. Cool. Questions on this one? Where's the question?
That's a good question.
No. It's up in the bottom.
What the heck? Frick, what did I just do? Oh. There we go. Alright. I'll just have to do it out of presenter mode. Okay. Can I still write? No. If I go back.
Is there a way to get it on like a clicker? Maybe it's like animated to appear.
I don't know. Does anybody know? Oh, maybe right here? Why does the solution come before the whatever? Okay. So this one's asking to find the inflection point. Okay. So not too bad. We need to find the second order derivative because inflection point concavity, second derivative. So our f prime of t is 132t minus 22 minus, this is the chain rule, e5 to the t times 5. All right. Then we f double prime of t is just 132 minus 25e to the 5t. Yeah? Because that would be, I took my 5, multiplied by that another 5 by taking the derivative of that again. That's how I got 25. Yeah?
Wait, so why did 22 become 25?
All
Oh,
right.
because 5 times 5. Yes. Okay.
Yeah. Does anybody want me to write it out? Okay. Cool. Then we set this equal to 0. 0 equals 132 minus 25e to the 5t. And so I'm going to switch them over. So it'll be 132 is now equal to 25e to the 5t. And e to the 5t. Oh, wow. Equals 132 over 25. I'm going to take the ln of both sides. So we have 5t is equal to ln of 132 over 5. Therefore, t equals ln of 132 over 25 over 5, which does equal this. So the calculus part, not too hard. The algebra part, more involved, but you guys can do it. You guys have done that before. So, yeah. If it makes it easier, you can split the natural log up. If you remember your log rules, if you prefer that, you get the same thing. Any questions? Okay, cool. So yeah, at 0.3327, at that point, the concavity switches from up to down. That's what the inflection point is. Cool. Okay, last question.
Okay, so we want to find how many minimums and maximums these have. Local ones, not global. So I'm just going to focus like completely on F and then we'll do G. So how do we find a min or max again?
find the first derivative and then set equal to 0, and then plug the values you get from that into the original function.
Right. Okay, so this one first, well, we need the first derivative for sure. So f prime, we get 4x cubed plus 4x squared minus 16x minus 16. Yeah? Okay, and then we have a few options. Do we want to do the second derivative way or just the first derivative? With like checking on our number line. Okay, sure. I'll show you that way. And we can try the other way for the other one if you want. Okay, so first derivative, we want to set this equal to 0, right? That will give us where our slope is 0. Then I'm going to pull a 4 out of everything. Okay, then we can factor this. If we remember how to factor one with 4 things, I usually like to split it into 2 and 2. And then this 4, we can just do 0 divided by 4 and get rid of it. So we have these first two, I can pull out an x squared and get x plus 1. Minus, here I can pull out a minus 4, then get x plus 1. Okay, and then since these are both multiplied by x plus 1, can just do x plus 1 times x squared minus 4. This x squared minus 4 we can actually split again. Get x plus 1 times x minus 2, x plus 2. So it's a difference of squares. Are you okay with the factoring? Okay. Cool, so then x equals 0, well, this function equals 0 when x is -1, -2, and +2. Okay, so now just doing the first derivative way, usually draw a little number line of -2, -1, +2. And I want to find something in between all of those to plug into my derivative to see if it's going down or up. So I'm going to say at -3 for this one. Do you guys want me to like write out the whole function or do you feel okay about plugging things in? Okay, yeah, it's going to take me forever to write these all out. So at -3, it is -40. So that's going down. And then between 2 and -1, I think I did -1.5. And there it is 3.5. So that's going up because it's positive. And then -1 and 2, 0 is usually pretty easy to do. That's -16. It's going down again. And then past 2, I just did 3. There it is 80. So up again. And then look here, we have 2 minimums and 1 maximum. Okay, so that's the first derivative way. The second way is just like taking all of these and plugging them into the second derivative to see if these are conjugate down or up. They're about the same amount of work, so whichever you like better. Okay, let's try the second one now. I'm just gonna get rid of all of this. Okay, so we're going to need the first derivative. So I'm getting 15x squared minus 60x plus 60. Okay. And then factoring, can pull out a 15 to get x squared minus 4x plus 4. Okay, then this one, we need something that adds to 4 to -4 and multiplies to +4. I think -2 and -2 would work. Yeah. Okay, so it looks like x just equals 2. Okay, so do we want to try the second derivative way or do it the same way? Okay, let's do it. So xg double prime, get 30x minus 60. Okay, and then we can plug 2 into that. 30 times 2 minus 60 is 60 minus 60, which is just 0. So it's not concave up or down. So do we have a minimum or maximum there? No. So yeah, this one just has nothing. Okay, questions on these? On either method? Oh,
Yeah, okay, so this was recorded, so in case you guys have any other questions,